Hi, so I'm Clara. I'm from the Space Telescope Science Institute and the MAST Archive, and I'm going to talk about making efficient cutouts from sets of TESS full-frame images. So TESS is the Transiting Exoplanet Survey satellite. It's a sort of a successor mission to Kepler. It was launched just about 2 years ago. We had the anniversary over the weekend. There's this picture here. It has 4 cameras, each of which has 4 2K by 2K CCDs. It observes in the blue to near infrared range and has really enormous pixels. So it's about 21 arc seconds per pixel, making for a full field of view that's about 24 by 96 degrees, and it's in these long strips. And so the main mission was planned for 2 years, although it has already been accepted for an extended mission. Its original plan was for 26 sectors, which is each one of these strips in the sky, lasting about a month. So that's 2 orbits of the satellite, starting in the southern hemisphere. Now it's observing in the northern hemisphere. So like Kepler, TESS provides a number of data products, light curves, target pixel files, and full-frame images. I'm going to focus on the full-frame images because unlike Kepler, which took full-frame images rarely, TESS takes them at a 30-minute cadence, and it's going to be even faster in the extended mission. So there's when it takes a full-frame image, it produces 1 image file per CCD, so that's 16 total, and it's about 35 megabytes per image, and that happens every 30 minutes. So that's a lot of data that builds up quickly. And that is great. It means that the TESS FFIs are a large and incredibly valuable scientific data set in and of themselves, and that it is in fact possible to do time domain astronomy just on the FFIs, which means you can use it for any object that's in the TESS field of view, not just the ones that were targeted for 2-minute cadence light curves. But one of the first steps, because these images are so large for scientists, and also if you're going to make these light curves from the FFIs, is to cut out an area of interest that's much smaller than the entire field of view or the entire CCD. And so one sector of FFIs for one CCD is about 50 gigabytes. And so as this data builds up, it becomes quite a lot. And so when we knew that MAST was going to get this mission and we're looking for ways that we could not just archive the data but provide more value to the community, we came up with this idea for a service that we called TESScut. And it had 3 goals. First, to provide a user-friendly way to get cutouts from a sector of FFIs. This is the prevent scientists from having to reinvent the wheel all the time goal. If almost everyone is going to need to do this first step, why don't we do it, and then everyone can concentrate on doing the science. 2, to eliminate the need for users to download the entire sector of FFIs, or not entirely eliminate the need for users who won't be using a large portion of these images. And this was a sort of win-win type of goal. It's a win for the users and scientists who don't need to download large numbers of enormous files in order to look at small parts of them. And it's a win for us as the archive, who don't have to stream out these large amounts of data and have it become slow just so that scientists can get small parts of it. And then the last goal was to return the cutouts as in TESS pipeline compatible file types, specifically a target pixel file. And this was, again, part of the not needing to have scientists reinvent the wheel goal. Scientists, even before TESS went up, even before TESS was a thing, these target pixel files are very similar to Kepler target pixel files. There are tools that ingest these files and do things with them. And so we wanted them to be able to just hook right into the files that come out of TESScut, as well as being able to work on the ones from the official pipeline. And so how this ended up playing out was in this sort of slightly more complex TESScut Astrocut ecosystem. And so there's 3 layers. So the bottom layer, which is actually on the top of the slide, is Astrocut, which contains the underlying functionality that allows the cutouts to happen. It works on the FFI files themselves and returns the cutouts. And this is while most of this talk will focus on how this functionality works for TESScut, Astrocut was designed as a package to contain a number of different cutout tools, and that can be expanded to other missions and other use cases. And so that solves the reinventing the wheel problem, but it doesn't solve the not having to download all of the data problem. This is a package that's available on PyPy. It's Python. You can install it on your own machine, but then you have to have all of the files there. And so that's where TESScut, the web service, comes in. So this is a RESTful web service that runs Astrocut on STScI servers local to the data. And so that's basically the fastest, most efficient way to make a cutout, and then just the cutout file that the user needs is streamed back to them. And then to make it even more seamless for people who use Python as their analysis language of choice, their MAST maintains a module in the AstroQuery Python package, which is designed for to allow access to archives and other web forms. And within that, there is a TESScut class, so that if you're a Python user, you can get these cutouts directly within your Python analysis workflow. So that's how it works from a user perspective. And what I'm going to talk about next is not actually anything you need to know to use it, but is really interesting, the design choices we made and some of the work we had to do to make this not just function, but function in a performative way. And so what happens under the hood is that there's actually two pieces. And the first piece you have to do once, which is where you make a cube from all of the FFIs of one sector. And then the cutouts work on that one enormous file. And so why do we want to do this? Well, we're trading basically one-time work for every time work. So instead of opening every time you make a cutout, instead of opening lots of files, usually between 1,250 and 1,350 files, you make one giant file, and then you only have to open one file every time you make a cutout. And then to make it even more efficient within that file, we've arranged data in the file in a way that minimizes seek actions when doing cutouts. So what a seek action is, in a file this big, even a single FFI, when you open it, you don't typically put the whole thing in your computer's memory. It reads the metadata and the FITS headers and the information that tells the program where the data is kept. And then it has to go, when you actually want parts of that data, it has to go and read that from disk again. So the minimum number of times you have to search for a specific location in the file and read some bytes, the faster it is. And particularly with large files, this starts to matter. And the reason we do it is that it makes a huge difference for performance. So without cubing, doing my best to make the code as efficient as possible, including parallelization and running 8 simultaneous threads for a relatively small 10 by 10 cutout over a sector of 1,350 images, the best I could do was about half a minute for a single cutout. And that's like maybe fine if you're just doing a couple, but it starts to be frustrating if you're doing a lot, and it's really not performant at all if you're talking about providing a service where you have, several users, many users, each asking for multiple cutouts all at once. We see quite high traffic on this, and the request would just back up very quickly. But with the cubing, you can add no parallelization, nothing special really in terms of making it efficient, and it takes about a second to make the same cutout. So that's obviously much better. It's much more scalable, but you do have to do that initial upfront work. And so the way we do that is the most obvious way to turn a set of FFIs into a cube of data is we pull off all of the FITS header information and we save that off separately. And that's small, and so it doesn't, it's not that it doesn't matter, it's important, but how we treat it doesn't really matter for performance. And then we take each image and we stack them into a cube. And so the most obvious way is to just stack one on top of each other. So I've visualized it here as a 3-dimensional cube, but of course, what we're seeing is it's the representation in bytes of one image followed directly after it by the next image and so on down through the time, which is throughout the sector. And so this is pretty good. Now we only have to open one file, but when we start to look through it, we have to, every time we have to find an edge of this cutout, which is the small core in the center, we have to do the same thing for every single time. And so very quickly we're having to seek for small bits of this enormous cube of data so many times. Whereas if we take that data and we just tip it on its side, which is obviously simpler in a visualization than to do in code, but you only have to do it once. Now, when we do the same thing, once we find where our cutout that we want begins, we can read many more bytes in a row that are all relevant to what we're looking for before we have to find the next place where that occurs. We can essentially read an entire plane of this cutout. And so we have to look for many fewer points in the file to read bytes, and it's much more efficient. And so that's the theory of what we're doing, but how do we do that in practice? And so in practice, what that means is that instead of writing one image followed by the next image followed by the next image, what we're interleaving them, so we have one pixel at every single time followed by the next pixel at every single time. And so what that means is that there's two trade-offs when we trade the one-time work. There's obviously the time we have to make this cube, which we wouldn't have to do if we weren't going to use it. But there's also memory. Because we are not doing it the simplest way, where we just write an image to disk and then write the next one and then write the next one, and instead we're interleaving, we have to be able to put the entire cube in memory once when we make the file. Once we make the file, we can run it on a system that doesn't have enough memory to store it in memory. But to make it, we need to have about 60 gigabytes of memory to comfortably fit the whole thing in memory. And it takes about 10 to 15 minutes to make one of these. So again, if you're doing it on your own system and you only want a few cutouts, that doesn't really make sense. You have to do this 15 minutes of upfront work and then it takes a second. Or you could just wait for 3 minutes and have 6 cutouts. But if you're talking about scaling it and running a service, or even if you're talking about doing it yourself and running it on a very large number, hundreds or thousands of sources, it becomes much more effective to do this work that we only have to do once for every set of FFIs, and then you get this huge performance boost for the rest of the time you do cutouts. And so most of the time, as a user, your first stop is going to be TESScut. You don't have to install the software yourself. You don't have to figure out how to use it. You don't have to download all the FFIs. It's straightforward. You can do a handful to several handfuls. You don't have to have any special amount of memory. You don't really have to wait. So that's great. However, if you want to do every cutout in the sky, or if you want to make really big cutouts, then you'll start to run into issues where you're running up against your bandwidth, and you're also competing with other users who are trying to use this service. It does have some limitations. And in that case, it probably does make sense to install the software. It's not very hard to install. You need a system with enough memory, but if you have that, you can download all the FFIs, make your own cube, and then you can go as fast as your system can go and everything is local. Also, if you want to do something non-standard, Astrocut is open source. It's on GitHub. You can fork it and you can change it to do whatever weird, fun thing you want. And if it's awesome, you can also just submit it back to us and we'd love to have it. So this talk has been around what happens under the hood, but when you actually go to TESScut to use it, you don't have to know or care about any of this. You can access it through a web form. You can use just straight up HTTP GET requests, so it does not have to depend on any particular language. If you use Python, it's probably easier to use TESScut, and they all access the same and make the same calls under the hood, so you're getting exactly the same thing back. It's just what works for your workflow and your analysis. And as I mentioned earlier in the talk, that's not all Astrocut can do. If it also does generic fits cutouts and image cutouts. And so these are, they're not optimized, they're not as, we put a lot of effort into making the TESS performance increases because we knew exactly what we were going for, and this is more generic. But you should be able to throw pretty much every any fits file at it. I mean, to be clear, it is currently in beta. We would like ultimately you to be able to throw every single fits file at it and have it perform a cutout. Right now, we think you can do most of the ones certainly from Hubble and our major space missions, but we would also love to hear about any fits files that it doesn't work on so that we can continue to expand it. And you can perform the same cutout on one or more FITS files. It currently doesn't do any orientation resolution checking and cannot do resampling, but we hope to add those things in the future. And you can also get the cutouts back as images. Again, no resampling, so you can't change the resolution of the image, but you can get a PNG or JPEG, and if you have 3 inputs, you can get a color image, as I have shown over here. So here's all of the places to get information on everything I talked about, and my information is at the bottom. I always like to talk to people about cutouts, and TESS is a wonderful mission. And any questions?
Hi, this is Michael. I was wondering how easy it is, because this is a standard problem in planetary science, to co-register the FFIs so that you build the cube correctly. Because if that would not be correct, then all of this cutting is, has the errors of the individual FFIs not being at the same coordinates as the other slice. This has to be, I guess, the most time consuming or most effort work that you need to do to produce a good cube.
Yes, and that was something that we were able to sidestep with TESS, because it has very steady pointing and its pixels are so big. So the changes between exposures are so small that they're much smaller than a pixel. But yeah, that is something I've thought about with expanding the same sort of it would be a reason that you might want to make a cube for something other than the performance, right? Because then you have to do the registration and the making sure the pixels are aligned once. And once you have that data cube, you've done that work, and it would probably, it would be the hard work, but you could definitely do it, and then once it's done, you can do all of your cutouts without worrying. Yeah, so currently that we don't do that because of the nature of the TESS mission. But yeah, that's definitely something that can be done, and I've done some registration of images and on a much smaller scale, but it would be interesting to add it to a sort of cubing functionality that then creates something that you can easily take pieces of, knowing that you've already aligned all the pixels.